Good afternoon, everyone. We'll start in class in 1 to 2 minutes' time. To answer that question regarding quiz 2 and quiz 3, you guys will get some advance notice on when we'll be doing those in particular. For now, what I can tell you is that quiz 2 is most likely going to be next week, but if that changes, I'll let you guys know on the forum. Quiz 3 may be way later down in the semester, but like I said, you will get advance notice when these quizzes are coming out. Alright, good afternoon everyone, and today's session we're going to be finishing up our sorting and searching algorithms lecture that was the last lecture from last week, and then we'll be moving on to the start of our data structures overall topic, and in particular we'll be revisiting stacks and queues, which was a topic that we did in year 1 programming, as well as linked lists, and we're going to see how each one of these operate in particular. Now, the concepts behind these data structures, they're very easy to understand, and the implementations of them are also very easy because they have very simple operations. But as we move on to advanced data structures later on, you want to see why these structures that we do here, which are considered simple data structures, how they build with each other to form these advanced data structures. So let's get started with our second sorting and searching algorithms lecture for today. And we saw that last week, the 3 algorithms that we did was the insertion sort, the selection sort, and the bubble sort. And in today's lecture, we're going to be doing the other 3 algorithms, which is going to be merge sort, quick sort, and bucket sort. We'll also look at one searching algorithm in particular, which tends to be very popular when it comes to programming interviews, which is going to be the binary search algorithm. And you have already seen this binary search algorithm in action in a previous lecture, where we saw that we could start off with an entire array, and then in order to find a particular value in the array once it was sorted, we just kept on dividing the array in half and searching each halves accordingly until we found that value. So merge sort is basically a divide and conquer technique where it tries to figure out how fast we can go about dividing the entire problem into subproblems, and then we can just sort each subproblem and then combine the result all together. It is one of the more popular sorting algorithms that you would see. The worst case time complexity is O(n) log n, which is not bad in comparison to our previous 3 sorting algorithms, where we had a complexity of O(n) squared, which was kind of horrible in comparison to this. And then you're going to see that most of these algorithms here are going to end up being a little more optimized than the previous 3 sorting algorithms, and some of these can actually be applied to large data as of such. So merge sort starts where you divide the array into equal halves, and then you start combining them in a sorted manner because you start sorting each one of these halves in. So the visual example here is that if we start with this unsorted array, and then we divide this array in half, so we have the first 4 elements as its own subarray, and then the next 4 elements as the next subarray. We keep on doing these divisions accordingly for each half as we keep on going. So instead of having 2 groups of 4, we now have 4 groups of 2. And then we keep on going until we get to only groupings of 1. And these groupings of 1 are referred to as an atomic element, where the definition of the atomic element meaning that is that there's only 1 unit that can be associated with it. So this 1 unit here is going to be 1 piece of the entire data array that we started with. So then, after we do all these divisions, we combine them in the same manner that we broke it down, and then we go about doing the comparisons here to figure out how do we go about sorting the entire thing all together. So we're going to see how this sorting and combining is done that forms our merge sort algorithm here visually. So we start with 14 and 33, which was our first 2 values that we had. And we see, okay, is 14 and 33, which one is the less value and which one is the greater value. And we put the less than values on the left hand side and the greater than values on the right hand side in particular. So in this case, 14 and 33 is already sorted. 27 and 10 are then compared, and then you realize, okay, 27 is greater than 10, so these two have to swap accordingly. The 35 and 19, the same thing happens, these two have to swap, and 42 and 44, it's already in order. So once all these swaps here happen accordingly, for each pair of values, this will be the end of our first iteration for our merge sort. So the result here will end up looking like this. Where each pair of values is sorted from the least most value to the greatest most value. So this was where we sorted values in pairs. For the second iteration, we're going to be sorting values by 4s instead. So we group the first 4 elements here, which have been already sorted to begin with. And then we group the other 4 elements here. And then we sort them accordingly to see, okay, which values here are supposed to be in order accordingly, the same way as if we were doing the sorting for our first 2 values. So once these elements here are compared accordingly, as of such, and they are sorted again, this will be the end of the second iteration where each grouping of 4 elements is going to be sorted from lowest most value to greatest most value. So you'll see here, this 10 will be the least most value, then the next following value will be 14, 27 here, and 33. Similarly, 19 will go here, then 35, and 42, and 44. An event if the array is an odd number length, it will be such that the groupings will end up being somewhat different in nature. So you will end up getting a grouping where you will end up having 3 elements as of such. And instead of like you trying to group in terms of 2, 2, 2, and 3, some cases you may want to change the groupings so that you get like an even split. But if you can't get an even split accordingly down to some minute number, they go about doing the sorts and as a result, so they'll have like 2, 2, 2, and 1. So they'll sort all the pairs, and then when they sort all the pairs, they look for the least most value in every one of the pairs, and then they compare it to the odd value that stands out, and they'll figure out, okay, where does this odd value supposed to be placed accordingly, and once they figure out where to place it, then they go about grouping accordingly and keep on going up in order until they finish the entire sorting. So that odd element that's going to be out of grouping is introduced in a separate way to go about sorting it accordingly with the other grouping. So once we group here in terms of 4 and we sort in terms of 4, this will be the end of the second iteration. And then the third iteration, we compare the elements into groups of 8 here. And then once they're sorted accordingly, we merge them into the final array as of such. And the end result here will be the sorted array that we require for merge sort. So merge sort is kind of like similar to your bubble sort that you saw earlier, where it does the swaps accordingly. Same thing like if you were seeing like the selection sort where we had the swaps. But instead of operating on the entire array, it breaks it down into sub-arrays. And it tries to group it in terms of pairs. If the array is odd in length, it will have an odd value that will stand up by itself, and it will do the sorting for the pairs accordingly, and then do a comparison of the odd value to see where it actually can lie, and it will keep on doing the sorting as of such. So this is basically the general algorithm for merge sort. And basically it just keeps on dividing the array recursively into 2 halves until it can no longer be divided, and it just sorts each half accordingly and then rebuilds the array accordingly for the sorted version that is required. The code for merge sort is actually provided on my learning, so I suggest that you guys download it and analyze it and see how it operates. And yes, it can work for odd values of the array length as well, so you can actually see how it operates step by step. Alright, any further questions on merge sort? Alright, doesn't seem like we have any further questions on merge sort. Alright, let's go on to our next sorting algorithm. So, quick sort is also a very popular sorting algorithm that you tend to see already have existing implementations in its own programming libraries for C++, Java, and other programming languages. And it's basically based on the same idea of the merge sort, but it operates a little bit differently, and we're going to see how it operates differently as a result. Okay, so before I move on, merge sort basically, instead of operating on the entire array, it breaks the array into subparts and it sorts each subpart and then reforms the array. The other sorting techniques that we learned operates on the entire array and it does not break it apart at all. Alright, so we're going to see how quick sort here is going to be a little bit different from our merge sort in a bit when we start watching visually. So quick sort, what it does here is that it uses something that we refer to as a pivot. And the pivot is going to be, how do we figure out what's going to be technically our midpoint of our subarrays. And everything less than the pivot will go onto the left-hand side, and everything greater than the pivot is going to be onto the right-hand side. And quick sort, because it uses this pivot value here, it's a little bit different than merge sort because yes, it does break the array into two subarrays, using this pivot value to know where to break the array accordingly. But at the same time, the left-hand side and the right-hand side do not have to be equal in length, depending on the value of pivot that is used. Now, quicksort is also very effective for large-size datasets because depending on the pivot value, it may be such that you may not need an entire section of data, and you can optimize which part of the data you wish to sort in particular using a specified pivot value to divide your data accordingly. The average and worst complexity, however, is going to be O(n squared, which is a little bit horrible, but depending on the value of pivot, it actually can improve quite dramatically. So there's an animated visual effect here indicating the steps of how quicksort operates. And you can see here that it selects a pivot value and it starts doing the comparisons around the pivot value in order to figure out, okay, which value is less than pivot, which value is greater than pivot. And it does the swaps accordingly to make sure that it knows how to go about doing these pivots. Once it figures out that it does all the swaps, it then puts the pivot value accordingly where it needs to be. So you can see here that 31, 35 is less than, and 26 was less than. So it puts everything that's less than the pivot on the left-hand side, and everything that's greater on the pivot on the right-hand side. It also does this by comparing pairs of values starting from the outermost into the innermost. So it started with these two, then these two, and then it compares these two accordingly as it keeps on going. And then it figures ways to insert the pivot after it does all the insertions accordingly. So for your homework here, and you know why, at this point, why I give you guys some homework, is to try to examine the animation and figure out how it works. And you also have the code provided to you on my Learning for Quicksort, so try to see how does it match back up to the code in particular. The general algorithm for quicksort is given to you guys here, which basically is going to match up to the code implementation that is provided on my Learn. Alright. Now, if there are any particular questions on quicksort, normally I would entertain them here in the chat, but because I'm giving you guys some homework, questions for quicksort will be entertained on the forum once you start attempting this to understand how it operates. But once you basically analyze the algorithm here, you'll have a good idea of how the animation matches back to the algorithm. Bucket sorts is also another popular algorithm that is used for sorting, and this is also referred to as the scatter-gather approach. And we'll see visually why it's going to be the scatter-gather approach in a little bit. And the reason why it's called bucket sort is that you'll see that these buckets here kind of operate similar to that of a histogram, where once the values lie within a certain range, it gets sorted into that particular bucket that specifies that range. And once these values are put into each bucket within the range, each bucket can be sorted using any particular sorting algorithm, because in particular, the values that's going to be inside each bucket, the amount of them is going to be small in nature. So you can choose any sorting algorithm to sort the contents of the bucket as required. If you wish, you can use the same algorithm for sorting each bucket for the entire algorithm, for the entire bucket sort in particular, sorry. And this is incredibly useful when you have extremely large data and it cannot fit in your available memory. You can go about sorting these in chunks one by one and then putting them back in order as a result. So it comes like if you're doing bucket sorts here, bucket sort is extremely effective for when you have limited memory and your data set is very huge and it cannot fit in your available. The best time complexity for a bucket sort is linear, which is going to be O of n plus k. I want you guys to figure out what the n is going to be here and what the k is going to be here in the next few slides. And that's also going to be part of your homework, to try and figure out what does the n represent and what the k represents for our bucket sort algorithm. So in the best case, you'll have a linear order algorithm, which is going to be O of n plus k. In your average case, you will have O of n. And in the worst possible case, which rarely occurs, you'll have O of n squared. So we're going to see two examples here that illustrate bucket sort, and let's see which one actually is better explained for you guys as a result. So remember, bucket sort here is a scatter-gather approach. So we start our initial array here with all our values, and we scatter it accordingly, such that each one of these buckets here represent the range of values that we want these values here in the initial array to be sorted into each bucket. So our first bucket here can only hold values between 0 and 5. So in this entire array, only one can go here. Second bucket can hold values between 5 and 10. So we see that it's going to be 9 and 8, and so forth for 10 and 15, 15 and 20, 20 and 25. Once we scatter the array here into its range buckets accordingly, we then sort the contents of the buckets to make sure that the contents of the buckets here are in order. Similar to the approach that was used for our merge sorts that we saw earlier on. But the contents of each bucket here is sorted. And once the contents here are sorted, we then go from the lowest range to the highest range in order and rearrange it so that we gather the values and put it back into order as required. The step-by-step example here is going to give us the in-depth explanation as to what actually occurs with each one of these operations. So if we have an unsorted array here, which is going to be 7 values in total, typically we can say, okay, these are some values here, but we're going to create an array here of size 10, and each individual slot in the array here is going to be used as a bucket for storing elements. So we're going to be inserting elements into each one of these buckets here, which are going to be slots in the array, starting with left to right here in order to get these values going in. So we can, depending on the range that we have here, we can specify what range is going to be for each individual slot in the array. So we can be like, okay, this goes from 0 to 0.1, this can go from 0.1 to 0.2, this can go here from 0.2 to 0.3, and so forth as we keep on going. And we can sort these values here accordingly into each one of these individual slots in the array. Once each of these elements are slotted into the buckets here, or each slot in the array, representing the range, the same thing happens as we saw in the high-level example. We sort the values for each slot using the sorting algorithm, and then we just offload each of the buckets in turn to form our finalized sorted array. So you see here, 0.23, 0.25, then 0.32 goes here, 0.42, 0.47, 0.51, and 0.52. The general algorithm for bucket sorts is given here, and the code for bucket sort is also provided on my list. Alright. Any particular questions regarding the bucket sort algorithm? Ask now. Yes, so depending on the data that's going to be processed in each one of those buckets, you choose a suitable sorting algorithm to sort each bucket accordingly. And that choice can actually be dependent on the nature of the data or how many values are going to be inside each bucket and so forth. So to sort the contents of each bucket, the suitable sorting algorithm to use, you can just choose which one in particular that you want to use based on these criteria. Sorting is not only used for arrays. What we're going to see is that when we move on to our data structures, there's also a way for you to use sorting for these particular data structures as of such. But the reason why we use arrays for explanation is that what you're going to quickly realize is that most of these simple and advanced data structures are basically just fancified versions of your simple array in just some different form or fashion. So once you understand how it operates for one array, it operates for all arrays. Close enough with the O of n plus k, but the explanation needs a little more work. So, as I say, think about it a little bit more, and there's a reason why I'm giving you that for homework. So, you got the n part correct. The k part is what you have to think about a little bit more. Right, it doesn't seem like we have any further questions on bucket sorting. Right, let's go on to our search algorithm, which we actually do have a little bit of experience on so far. So we actually seen this binary search algorithm in practice, and in particular we saw it in our complexity lectures. And we're going to be talking about it here in a little bit of detail, so we can get a better understanding of how it actually works. So binary search is also a divide and conquer approach that we go about doing. And it's also one of the most popular search algorithms that is used in industry because of its nature and how fast it actually can operate in particular. The next loop for sorting, yes and no for answering the bucket search sort approach, but like I said, think about it a little bit more. And if you got any further questions regarding that, I'll answer it after once I finish each for today. So the average and worst time case complexity of binary search is O of log n, and we saw in particular that when we did the analysis of this in our space and time complexity lectures, that log n approach was where we had a constant division by some sort of factor. So that's how we end up getting this order complexity here for binary search as a result. And the keyword here being binary is that binary only can take two values. It's going to be 0 or 1. And because of its only two values, that means we'll always be dividing by halves as we keep on going throughout our entire search. Now, before binary search can actually be done, your array needs to be sorted either from lowest to highest or highest to lowest. And then you can actually do your binary search effectively. If the array is unsorted, the binary search is going to take extremely long. And as a result, you may end up getting wrong results accordingly, or that you just end up taking like 3 or 4 times the amount of time just to try and find a particular value because it's going to be obscured in some form or fashion somewhere. So remember that binary search can only operate once the array has been sorted either from lowest to highest or highest to lowest. So in our particular example here, we have a lowest to highest sort. And let's say we're searching for the value of 4 here in particular. And doing binary search, you need to set 2 pointers for the lowest most value and the highest most value as a result. We then find the middle value from the lowest and the highest by observing the positions here and the length of the array. If x here is designated as the value that we are searching for, if it's equal to the middle here, we return that value and basically we stop searching because we found a match. If it's such that the search value here is greater than the mid value, we search on the right hand side, and if it's going to be lower than the mid value, we search on the left hand side. So in the event where our search value here being x is greater than the mid value, we will be comparing x here with the middle element of the right hand side of mid. And as a result for this particular case, we had our, I think I'm going to have to correct this, our lowest most value here, no, this is correct, sorry. So we go about setting this so that way low here is going to be mid here plus 1. So that way we're only searching on this side here. So when we do this, in particular, I'm going to annotate a little bit. The original low was here, but this is going to move to here instead. And this pointer here will still remain high. So we only be searching here accordingly as a result. If it was that, in the event that our x value here was lower than the middle value, we need to move the high pointer that originally existed here to match to the lower half accordingly for our search range. So just to re-annotate, what this does is that originally we had high here, but then when we do this, we move high here to this point, which is less than our mid value, indicating the range of values that we need to search for as a result. So in moving the low and high pointers here, we reduce our search range accordingly each time. And in the reduction of the search range that we keep on doing, we end up doing this until we actually find our value as a result. And eventually, we will end up finding the value that we search for. So there are two ways to go about implementing binary search. There is an iteration algorithm, which is highly effective, and it's a simpler one to learn. But there's also a recursive algorithm that is preferred in certain cases. So in your programming interviews, typically you can choose one or the other because they'll just ask you how you go about doing a particular implementation of it. But it also is very helpful to know both implementations, because there may be in a case where they say, okay, for this particular application, we need to use a recursive implementation of the binary search. Or for this particular implementation, we need to use the iteration version of it. But it's very helpful to know both versions because they can be advantageous in certain situations. So the code for both the iterative and recursive binary search algorithms are provided on my learning, so you can actually see how it matches back to the algorithms that were formulated here on the slides. And just concluding regarding our sorting and searching algorithms lectures, we need to know when to use which particular sorting algorithm for different types of situations, depending on the size of the array, how much data we're operating with, how much memory we have available, and so forth. And we know each sorting algorithm has its advantages and disadvantages in certain types of situations. Searching algorithms can only operate on data once this data has been sorted from lowest to highest or highest to lowest. And the most used sorting algorithm, the most used searching algorithm that is popularly used and is one of the easiest ones to implement is the binary search algorithm. We saw here that binary search keeps on reducing the search range each time when it does not find a match. So it does the search on the left-hand side and the right-hand side accordingly and keeps on repeating the steps until we find that match, effectively dividing our datasets by half each time until a match is found. Alright, so are there any particular questions regarding the contents of this lecture at this point? So this brings us to the end of a sorting and searching algorithms lecture and topic. Alright, doesn't seem like there are any questions. So, in addressing the last question there, remember N and K here are going to be different lengths of different things regarding your bucket sorts algorithm. So, you had the idea where N is going to be a static length, N is going to be the length of the entire array that you start with. But K also needs to be the length of something else, and that's going to be the maximum length of any particular bucket, which is compared across the lengths of all the buckets. So that's why you end up getting O of N plus K as a result. So yes, you had the idea with the loops, how it goes about doing that. Remember, you need to also define what N is and what K is with respect to data sizes in order to finalize your full explanation. Alright, let's move on to our data structures topic in particular. Close this off, I'm keeping my ink annotations here.